Hello, everyone. Daniel, thanks for a great talk. I really appreciated that. I'm using Rust for mine, so sound, but not complete. My name is Thomas Eckert. I will skip forward here and go to my intro slide. So my talk is listening to the radio with Rust. So I am a software engineer at Redpanda Data. My background is actually in physics, and I am a serial hobby picker-upper. Cycling, climbing, home lab, watercolor, and now software-defined radio. Does anyone here have experience with software-defined radio? Any radio, some experience? Very cool. This is something that's pretty new to me. And when I find something cool, my first instinct is to share it. So I'm actually not coming at this from the perspective of an expert. I've been doing this for a few months, and the goal of this talk is really to show you some cool things you can do, how to get into something like this, and how it's working. It's super accessible from the standpoint of like a price point. The device that I'm using tonight cost me like $30, $40. But it has a learning curve when you get started. So my goal is also to just kind of take you through that early learning curve, and if this interests you, you have a place to jump off of. All right, so here's what we'll cover. I have this talk structured going from the physics of the system here. So what's physically happening in the antenna? And then we'll talk about instrumentation. What is the dongle? I have it plugged into my computer here, but what is it actually doing? And then the interpretation of that signal. So, and then how different information is pulled out by interpreting that raw signal differently. And finally, I have a couple applications. So I have some live demos, so cross your fingers. So I have a demo of FM radio. I have a demo of using AM radio to listen to air traffic control. And then also ADSB, so that's a digital aircraft tracking. So kind of dependent on how many planes are in the air right now. But let's start with the physics. So I want you to imagine that there's a bobber that's sitting on top of a pool of water. And you push it up and down, it oscillates, and waves radiate out from it. This is what happens when a charged particle accelerates. So, for instance, an electron. It radiates out electromagnetic waves through space. Now imagine a second bobber sitting in that same pool some distance away. As those waves reach it, it will begin to bob up and down with that same frequency. The waves reach it, begins to oscillate, and driven by the energy carried on the waves. So this is the receiving antenna. Electrons in the metal are pushed up and down, and it induces electrons in the metal are pushed up and down by the incoming electromagnetic wave, and then the antenna converts that back into an electrical current. So I made a little demo of what that might look like. You can see here on the left, that is your transmitting antenna. It is moving electrons up and down, producing electromagnetic waves. And what this antenna is doing is the electrons are then pushed along on the incoming EM wave. Now everything that follows here is about how do we measure and interpret that movement in different ways. So today I'm going to talk about this dongle, software-defined radio, which digitizes a chunk of the spectrum, and then we do everything else in software. So this same dongle will receive FM, AM, aviation, ADS-B, and you just change the frequency and how you interpret the output. So I have a little diagram of what this chip looks like, and when let's see if I shrink, there you go, that's dealing with text. So there's two important chips in here. There's the R828D tuner, which selects what part of the spectrum to listen to. And then there is the RTL2832U, which is an analog to digital converter. So, what is the tuner doing? The antenna is picking up everything all at once. So the actual waves in the antenna it's a superposition of all incoming electromagnetic frequencies. So the R828's job, the tuner, is to select a narrow slice of that spectrum, and it shifts your chosen frequency down to the baseband, which is a low frequency centered around 0 that the analog to digital converter can sample. So you have all these different signals coming in. You're actually going to take that. There's an oscillator in the device that will then tune the oscillations in the antenna back down to 0 around that frequency that you care about, and then you're just oscillating about 0. And it's much easier to then sample that with the ADC. So if you think of it like a radio dial, you're not filtering out stations, you're sliding down the window so that your station lands at 0. And the dongle actually streams out raw bytes over USB. And one of the tools that I'm using on my machine to build applications is RTL TCP. So that'll take in the raw bytes from USB and then serve them over TCP. So you can write multiple applications that are tuning into the bytes that are coming out of the device. So for all of my applications, you have the RTL SDR, which is the particular device that I'm using. That goes into USB, and then that goes over TCP, and then you write code. You get a stream of bytes, and you can do cool things by reading those bytes in different ways. This also means that any program on the network can receive samples and also send messages to the device. So you could set this up on a Raspberry Pi and then remotely form some connection with it and start tuning. So we know that we're getting bytes out of this device. They're coming over TCP. What do they look like? So we're going to talk about IQ signals. So a radio signal at a single frequency is a cosine wave, like we saw that nice wave, right? And the tuner shifts it down to baseband, so it's around 0, oscillating at that level. And then we want to capture the amplitude and the phase. So we actually have to sample along 2 axes. So we have I, which is in phase, which is the cosine component. And we have Q, which is quadrature, which is a sine component. And then together, I and JQ is a complex number that encodes the amplitude and the phase of the signal at each moment. Now this can be a little mathy, a little heady, so I have another example. On the left here, we have the raw signal coming in. And on the right, we have how that gets represented in a binary format. So we are circling around the origin of the complex plane. And you can see here, so what I'm going to do is change the frequency. So if I increase the frequency, you can see that this rotates faster. So the speed of that rotation around 0, and for context too, the bytes that we are getting in are points that this traces out, right? So the speed that you're rotating around the origin is proportional to your frequency. If the frequency gets larger, then it spins more slowly. And then also the amplitude is the distance of those points from the origin. So if we have some kind of amplitude modulation here, we'll see the actual amplitude then changes the points that we're getting. So we're getting these points that are rotating around the origin in the complex plane. So the dongle outputs those pairs of bytes, and it's going to output IQ, 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 just in series. And like I said, each point, or each pair, each IQ point, is a point on the complex plane. And so we saw that rotation being traced out. And like I said, the speed of rotation is proportional to the frequency. The distance from the origin is proportional to the amplitude of the wave. So this is the key insight. So everything to do with SDR is about how do you demodulate out the data from that IQ signal. And we're going to go through some demos of different ways of interpreting that IQ signal. So first, I want to show you, and I should go through these one by one. So this is RTL TCP. This is running. I already set it up. I'm actually going to restart it because sometimes just restarting stuff just increases the likelihood that it works. RTL TCP. Cool. So that just connects to the dongle here, and it starts broadcasting the bytes that it receives over TCP. And what I'm going to do here is task IQ. Let me just remember. Task IQ print. Task IQ print. Okay. So here, this is printing the raw values. These are those points that are rotating around the origin. And it's printing a sampling. It gets way too many to print all of them. But you can see that we're printing, I guess I lose the header there. But you can see that if you were to plot these points, you would see that rapidly spinning around the origin there. All right, so I'm going to show you the first demo, and then I'll explain how everything works with it. So we take those signals. That is the raw data that's coming in. And now I am going to play you FM radio, 91.5. I don't know what 91.5 is.
CBC.
That's what?
CBC.
CBC.
Canada, and this is bad news for all of us. With less local news,
Just coming in through here.
rumors, and misinformation fill the void. And again,
There you go. We're listening to CBC. Okay. How did we do that? We took that... Oh, you have a question?
I'm just figuring out what is the sample rate. It's like 2 gigahertz.
Yeah. Yeah. So now I'm going to talk about how did that thing actually work. All right. I have to make sure that I'm reading code. So, all right. So we'll start off with those raw bytes. So that encodes that IQ data, and then we need to center and scale it. So this is that first step. We take the bytes and we get just the IQ values as a pair. And let me just... There you go. So we take those samples and then we take them pairwise and normalize them so that 127 goes to 0, 255 goes to 1, and 0 goes to -1. So we're on that unit circle. And then... So I can't quite see the screen very well, but we have many signals and we have one idea. So all the different signals sent over the radio are interpreted through different methods of demodulation. And like I said earlier, they all come back to measuring either the rotation speed or the distance from the origin. So actually, before I walk through all of the code for the FM, I want to show you a couple different things that you can tune into or build things around. So, and their frequencies. So there's AM broadcast, which I think we're mostly familiar with, where we're getting audio out of that amplitude modulation. There's ADS-B, which I'll give a later demo on. That's aircraft position. So all of the airplanes twice every second broadcast their position, call sign, all this data. There's OOK, which is usually like garage doors, and then there's weather stations. And a cool one I haven't quite figured out a good demo for, but there's satellite weather images that are encoded in binary, and it's actually very similar to like how fax machines work, but you can see these were originally developed for vessels at sea, for ships, because like
Storm coming.
yeah, exactly. So that's, like I said, this is also new to me within the past couple of months, so there's definitely gaps in my understanding. There's FM broadcast, so we just listened to that. That's audio. That's probably what we're all most familiar with, is FM radio in the car. FSK is for pagers and telemetry, so a digital signal. AIS, you can actually see ship position, so that one doesn't do much here because we so pretty. I don't know if we can reach anything. I don't know, but there are websites you can go on that'll show the position of all the ships in the world because they broadcast their position. POXAG pagers for text messages, and then there's like various digital voice, encrypted digital voice. But yeah, go back to IQ samples, demodulate, process. They all work this way. So the demodulation step extracts a meaningful signal from the IQ data, and then the processing step does something with it. So we'll see the FM radio, I demodulate the phase, and then I play audio. That's what we heard. AM radio, demodulate the magnitude, play the audio. ADS-B has several more layers because you're demodulating the magnitude, and then you're getting the bytes out of that. And then you have to decode that into the aircraft positions. All right. So why would you do this in Rust? Rust is not the only option here. But at 2.4 million samples per second, every sample gets about 400 nanoseconds of processing time. So you want something that's relatively fast. C would work. There's lots of languages that would work. There's kind of another hidden reason here, which is I will find any excuse to write something in Rust. But really, there's no garbage collector. There's zero cost iterators. There's good complex number math, and you can read samples on one thread and play audio on another, and have a buffer that shares between them, which is what I do with both the AM and the FM. So it's comparable to C with some of the convenience and readability that I prefer. And then there's also really great crates. So crates are libraries in Rust, external code that you can pull in. So a couple ones that I've used in this there's RTL SDR RS. So you can actually, I'm not using it tonight, but there's a pure Rust driver for this dongle. Complex numbers, fast Fourier transforms, cross-platform audio output, which is actually harder than you think, and then also Ratatouille for the little tuies that I built, terminal user interfaces. So there's no C dependencies. Everything just compiles with cargo build. And then I've also used tools like GNU Radio and SDR++, and they're more capable than what I've built. This is building it for the sake of building it. But my goal here was to kind of understand what's happening. Okay, so now I get to talk about how the FM radio code that I played earlier, how it actually works. So we have these IQ samples at 2 megahertz. We first do a low-pass filter, and then we decimate. Decimate just means decimate by 8x, take every 8th signal, right? There's certain limits to how much the quality of information that we're going to get and the quality of what we can hear. And then I do a demodulation, and then I do another low pass, and then I decimate even more because just the nature of the quality of what we can even hear from FM radio, and then do some de-emphasis, and then I put it out over the speakers. So let's look at that first step with the filter. So the antenna hears every station at once. We filter to just our channel, and then we decimate. And so IQ filter process. So we're going from 2 million samples a second to 256,000, and it's just less data to process. And we don't need all the data. The next step here for demodulation, this is where we're taking the IQ signal. So the input here you can see is that the array of complex numbers, and we are actually getting the data out by comparing every step with the conjugate of its previous step. So that's how you get like what's the speed of your rotation there. And you extract that angle, we get the kind of instantaneous moment frequency, and we scale it. So now what we get out of here is a vector of 32-bit floating points, and that's an audio signal at that point. And then we just need to take that and so what's really cool is like anyone could build this. The audio is the rate of phase change. Like it's just in there physically. There's no mediator. There's no like it just is there. You could discover this on your own if you kind of were messing around long enough. So if we look at filtering and playing the data, so we have our audio samples per second. We only need 48,000 samples per second. So we filter out the frequencies above 15 kilohertz because we can't hear them. We keep every fifth sample, and then we send it to speakers, and that's the whole FM receiver. How am I doing on time? Good. Cool. Does anyone have a favorite FM channel that they want to listen to? We can tune it again. So if I just do task, I can set that frequency.
88.5.
Yeah, let's do it. 88.5. Doesn't come through very well. I had some other ones that I was testing out earlier. And if we do... You can see all of my commands. 106.1. Oh, music.
That's the truth. I'm Heather. This is Ottawa's rock station, Shea 106.
Okay, so that's frequency modulation. Now you understand that whole stack. That's all that complex stuff that it's doing really quickly. And now we're going to talk about AM radio. So it's a similar pipeline. The change here is the demodulation, right? So FM, frequency modulation, AM, amplitude modulation. So if we look at that change, this is that process. We just, it's way simpler. I would assume why we did it first. We just take the square root of, this is Pythagorean theorem, right? What's the distance of the I and the Q from the origin, and then we create a signal from that. So much simpler. We're going to tune to the Ottawa airport tower. Receiving is legal. The law restricts transmitting and sharing private communications, but ATC is a public broadcast. Now, this is where we see if anyone is landing right now. I'm also just going to restart this real quick. Task RTLTCP. And we're going to look here. Task AM. So 118 or 118.8 is, I have a list here of all of the Ottawa aviation frequencies. That's tower. So we're going to cross our fingers that something is going on. AM doesn't encode as well. Like, that's why all the music channels are FM. You can get way more data. So let's see. I actually have... It was over here. So... there we go. Nothing's really happening right now. When I've done this in the past, I've like set it up for like 10 or 15 minutes, and then you hear somebody come through, and you're like, ah, I heard that. Like, I captured that. But it doesn't demo as well, because we're not going to stand here for 10, 15 minutes. Huh?
Can you hear Montreal from here?
Maybe. We should try it sometime. Actually, one of the funny things I had, I did not grow up speaking French. I accidentally tuned into the French tower because the Ottawa broadcasts both a French and an English tower, and I was like, this is garbled. Like, I can barely figure out what they're saying. And I was like, oh, it's in French. I was like, I can.
Do they have two towers transmitting in different languages?
When you are incoming, you can request what language you would like to be routed in. All of the Canadian, I don't know if it's just Ottawa. I know Montreal, you can do that.
I request French, and I tune to the French tower.
Yes. Yep. So they have those working in, but I believe that it's the same people, but to do ATC, you have to be able to do it both in French and English.
Just for fun, can we try 121.15?
Yeah, of course. AM?
AM, yeah.
All right, 121.15. What is it? Yeah, I've listened to the weather report, and it'll come through every now and then. Yeah. And sometimes it can be like the fact that we're facing north right now and the airport is south of us. Like, it's kind of fun to be back where like it matters. Like, you know, where you what's the cloud cover? What's this or that? And sometimes it's going to be great, and sometimes it's going to hear mostly static. But
The frequency is the same as for FM, so it shouldn't matter.
no.
But AM radio was always different. When I was a kid, I would listen to Cleveland Indians baseball games on AM because
Yeah, it goes way farther. Yeah.
But it was only with certain weather
Yeah.
and FM.
Mm-mm. Yeah, exactly. It's much more localized. But you know what? Like, sometimes I'll put it on in the background, and like I'm like doing some coding or something like that. And I'm like, oh, cool, somebody's talking. Yeah. I don't know. It's fun.
Can you try 119.9?
Yeah.
The last one? That's the Montreal.
Okay. Let's see if we get Montreal.
We're facing north, right?
We are
Frequency is too high.
9.9.
9.9. Is it too high?
Yeah. That's you don't hear Montreal FM, you don't hear Montreal FM. Bounce from some
Yeah.
atmosphere layer, but no.
Okay. Very cool. But it's fun to mess with. Like, you could just plug different things in, and suddenly you start hearing somebody talking, and you're like, wait, it's wild. Okay. So let me pull my notes back up here. How am I doing on time?
15 minutes.
Oh, great. All right. So the full AM loop here is you take that filtered IQ and you do the very simple demodulation process, and then you process the reels and to audio, and then you push that to your audio ring buffer and get the sound out. So even when it's just fuzzy, it's still doing something cool. But yeah, the only difference is how you demodulate. And then both produce audio. We're actually going to look at one last one. This maybe is a little bit too repetitive, but so we're now going to look at my last demo, which is also air traffic dependent. So let's go see. Oh yeah, I have it over here. Let's go see. There's not a lot going on.
Someone is approaching. Someone's coming.
There's somebody flying away over here. We'll see. But one thing to talk about. So I'm gonna do ADSB. Does anyone have an idea of why I want to shorten my antenna for ADSB? Why would a shorter antenna work better?
Higher frequency.
Yeah, but then what? Like I could receive ADSB here. Why would it be not as good?
Something about trying to catch resonance.
Yeah. So it's like it's because of the higher frequency. The you want to tune to 1/4 of the wavelength, and that's where you're going to get the best signal. And higher frequency. So I want to tune. This is a 7 centimeter antenna. It's pretty tiny. But what happens in that bigger antenna with these higher frequencies is that there's destructive interference because there's so many that single like really high frequency. You're getting destructive interference over time. So, all right, let's see if we can catch this plane. So this demo is the most complicated one, and there's 2 parts to it. So we have the ADSB receiver. So I'm going to start that. Actually, I am going to restart this guy, task, RTL, TCP, and then my receiver here, task, ADSB. ADSB is the name of the protocol. All right, so we're now listening for aircraft. And so what this code does, I can just keep this running. So there's 2 parts to this, right? This listens. Okay, give it its best opportunity here. What are we listening for, right? So every aircraft has a transponder, and twice every second, it broadcasts its position, altitude, speed, and a call sign. And so we don't have any that we see yet, but like when you look at tools like Flight Tracker, that's what they're tracking. So we might be able to see this guy is broadcasting, and you can see that they have, so they have their registration, they have their, so what they would broadcast is, CJT 619, and their altitude and everything like that. So we might be able to track them. This is fun to do to compare. So what I have here is that this will read in and listen for transponders, and then it saves them live updating to a SQLite database locally. And then I have a second application that I built with Ratatouille that is a map, and as we track airplanes, they will actually show up on this map, and then you can see them move over time. And like when it works, it's really neat. And so we'll see if it works, and I'll keep that running as I kind of answer some questions. We'll leave that running for a little bit. I want to see if we find anything. And I'll answer some questions. So please. Yes, go ahead.
one very stupid question. And one
It's great.
stupid-
No, that's
stupid
because I'm at
Yeah,
the beginning of this
first
too.
one- Okay, so in terms of amplitude modulation, like, what does so we have audio is like a frequency, right?
Yeah.
So if I have like let's say I don't know, some A440 hertz or whatever.
Yeah.
Very quiet versus very loud. How would that look differently in amplitude modulation?
Ooh. Yeah. So the question is, let's say that you had a concert A, 440 hertz, or a concert. Is that a C?
I don't know. Maybe it's a C. I don't know.
440
Just, it doesn't really
C.
matter. Just some
Yeah.
tone.
Hertz. Some tone. How does the volume of that frequency come through? This is a great question. I don't readily know. Does anyone have any ideas?
Modulation.
Yeah.
So in AM, it's just the height of the wave changes. The carrying wave is way more frequent than the signal, than our 20 hertz that we hear, 20 kilohertz.
Mm-hmm.
That's why for every change in the amplitude of this wave, we will receive many AM waves of different height, or the same height.
Mm-hmm.
And that's how we just sample this frequency, and then we just measure its amplitude, like Thomas showed us. Very simple code, distance from the center, that's awesome.
But, oh yeah, go ahead.
One of the things that I find really easy to think about this is like AM is not just taking audio and putting it onto into a radio wave just kind of by itself. There's a carrier frequency, which is like, imagine that you have like a constant frequency that happens, and if you're not playing anything, you have just this frequency.
Yeah.
And it's it's a sine wave or cosine wave, whatever the case is, just sort of like playing by itself, nothing's happening. When you add sound to that, it causes that fixed carrier frequency to gain and lose amplitude in proportion to the audio. So you can imagine the carrier frequency is sort of going up and down at like unit
Mm-hmm.
size 1, let's just say for sake of argument here. When you're doing nothing at size 1, when you have some amount of audio added, it goes to size like 1.5.
Yeah.
You play louder at size 2, so your sort of peaks get higher and your troughs get lower.
Okay, so I'll repeat that for the recording. So the insight there is that there's always a carrier frequency, say some cosine wave, that then gets modulated. And so if the input is louder, it will be modulated more? Higher amplitude. Relatively louder.
And it's obviously like, this is a bit simplifying as well. I'm not a physicist, right? So take this with a grain of salt. But
I think no sound means zero amplitude. That's why we hear noise.
So zero bit would be your carrier wave has what's called a base DC signal.
So the carrier wave is a base DC signal, okay.
Base DC signal, let's say like at +5.
Okay.
Right? And then you add audio on top of it, and then you basically do biasing,
Mm-hmm.
and to bring it back down to 0,
Mm-hmm.
that is how you extract, let's say, audio from amplitude.
Yeah.
And whereas in frequency, you have a base carrier frequency of, let's say, 5 hertz or whatever, and then you're actually changing it from 5 hertz to 5.5 hertz, so it's actually oscillating faster to encode the audio,
Mhm.
oscillating slower around that frequency. So that is the core difference. But in all cases, you do have the base frequency of the thing.
Yeah.
And depending on how powerful your transmission tower is, that determines how far your wave goes.
Mhm.
Yeah.
Mm-hmm.
And,
Very cool. Thank you. I'm glad that we have some people who are more experienced than I am in the room. Did that answer your question?
Yes, and the second silly question,
Please.
the other dimension is, have you ever listened to a satellite image?
Okay. You can. It doesn't sound great, but yes, you can do it.
I don't want to do this, man. That sounds fun.
Yeah, yeah, yeah. I have listened. So I had another demo that I wrote up, but it wasn't working with my antenna length. So this is something that's kind of cool about Ottawa specifically, is we have an atomic clock in Barrhaven, and that atomic clock produces. So there's a time signal. So it's encoded in English and French. You can hear the audio. And then there's also a digital signal in there that you can decode to get the accurate time.
I have a
I read on the news that they were going to stop something like that, some broadcast.
Really?
That was for radio stations.
For radio stations. Okay. Okay.
But you can buy a clock that
Yeah.
synchronizes to it.
Yeah.
You don't have to just a class for DST
No.
anymore.
Oh.
One, but this one doesn't listen to the Canadian signal, listens to the Japanese signal.
Oh, interesting. Okay, very cool. Your watch on your hand
Yes,
listens
it's
to that.
a
Yeah,
wristwatch, yes.
very cool. Yeah, I've seen one. I remember the first time I saw one. It was like auto setting the time. It's super cool. And yeah, I have a demo that works sometimes that you can get the current time from the CHU station. So pretty neat. But if you listen to that too, you can hear the audio, but you can also, if you listen to the digital signal, you'll hear it as like beeps. Yeah. Yeah. Yeah, any more questions? Yeah, go ahead.
Can you transmit? And if you can't, how?
Uh,
What's the next step?
I cannot transmit because I don't have a license to. So you can...
I just,
No, it's cool. It's cool. So the question was, can I transmit? Somebody can transmit in Canada by getting a license. I know we have at least one ham radio licensed person here. Radio stations for FM and AM, you have to get another permit for that. If you start transmitting without getting a permit, they'll find you because you're broadcasting your location. But yeah, what's the process for ham radio in Canada?
Yeah. I will do a very short summary, and if anyone wants to, I don't want to take up too much time. So
Yeah, no, this is great.
You can transmit in Canada in two cases. Either you are licensed to transmit on a particular frequency, and they're typically allocated in bands. So you have like a section of the spectrum and you get a license for it. For example, I as an individual cannot get an FM transmission license. It does not. They will not give me that. I have to be a corporation to do that. You have to have a lot of regulations around that. I can get that as a ham radio operator. There's certain bands I'm allowed to transmit in. There's also what's known as unlicensed, sometimes called ITU bands, ISM bands, where essentially it means like you can use the band without a license as long as you're using a valid transmitter.
Oh.
Like cordless phones are the classic example. You don't need a license to operate a cordless phone. It transmits in the 900 megahertz band. You can buy one from Walmart, pick it up, use it. Totally fine, totally safe, allowed to use that.
Okay.
So, as a Canadian, if you want to transmit some sort of radio, if you want to transmit arbitrary things, you need a ham radio license. Typically speaking, the transmitters you can buy to use on unlicensed bands.
Mm-hmm.
The transmitter themselves is what's licensed. That's the sort of chip that goes in the cordless phone or whatever. That stuff doesn't let you transmit arbitrary stuff. It only lets you transmit what that transmitter is licensed to transmit.
Right. So I'll repeat that. So for ham radio and for FM stations, you have to be licensed.
AM and so on.
AM and so on. And for ham radio, you're allowed to broadcast on certain frequencies.
Yes.
And then there are also unlicensed, or what was the some kind of band?
Yeah, I believe there's, I'm calling Canada here. I think they're called, ISM bands.
ISM bands, and these are ones.
Scientific and medical is the type.
Okay, industrial, scientific, and medical bands that you can use without getting a license. So the example used was cordless phones.
Yeah.
You don't need a license to use a cordless phone. I can't imagine what that process would look like if you had to. Very cool.
Yeah.
Very cool.
And there's a lot more nuance to it. There's other stuff like a walkie-talkie is technically not an ISM band. It's actually something else.
Oh, okay.
So like there's a whole bunch more nuance to this that like if you take the ham radio tests, they actually quiz you on the right regulations, which is not at all surprising. So you end up with a bunch of very useless knowledge about like how Canada operates.
Yeah, I was telling the story. As I got into this early on, my buddy is into ham radio, and he was walking me through that process of like the early kind of my dumb questions, which I think is a really important step in the learning process. And we were on a Discord video call together, and he was walking me through the different things. And towards the end, he goes, "All right, tune to this frequency." And then he went on his ham radio. He's on the coast of Maine, and he's like, "Hey, Thomas, how are you?" And it came right through. And it felt so cool. And it was like, I was trying to kind of justify it. Because like we were on a, HD video call going over the internet at the time. But like, he has an antenna. He accelerated electrons in his antenna. No mediation between us. I just picked it up and could hear him talking to me. It's cool. It's just fun. Yeah.
I've heard Croatia.
Yeah. can get pretty far. All right, looks like we're out of time, and we did not find any airplanes. But if you are interested, all of the slides, all of the code, everything here is on an open repository. There. It is my name, my handle, T-Eckert. Listening to the radio with Rust. You can take a picture of it. There's even more demos on there. You can just mess with it. Yeah, it's all public. The airways are public, so you can go listen, and it's all free. So, yeah, check it out. All right, thank you very much.